So hello and welcome to the third video for this third class in the exobiology from the Big Bang to the appearance of life on Earth. And in this third video, in which I talk about the second part of the class, I want to cover the formation of planetary systems. And here's an outline of what I'll talk about. The importance of this for exobiology. So why are we talking about the theory of the formation of planets? This is an especially important question given that we can now detect exoplanets. The initial conditions that lead to the formation of a planet, a planetary system and star, the formation of the disk, the evolution of this disk, and the timescales involved in these processes, and finally just a word about the glass line, which will be important for the discussion of where water comes from on Earth. And the material to support this class is principally this video lecture by the researcher Aurélien Crida, which you can find on this link on YouTube. And also this book that we used for the first part of the class by Crida. And I also used the book, an astronomy textbook called The Dynamic Universe. Might be hard to get a copy of that for you, but I would say that any textbook on any introductory survey textbook on astronomy should have a chapter at least on formation of stars and planetary systems. It's the same process. That's the main point of the lecture, actually. Spoiler alert, the stars and planets are formed together in one process called the planetary system formation. Okay, a few words about why we're talking about the theory of the formation of stars and planets. Remember that as exobiologists, we're coming at this from the point of view of exobiology. We're just interested in the abundance of shelters in the universe, or places in the universe where life could form. And unfortunately, we're limited to life as we know it. So we're going to look for shelters that would be hospitable for life as we know it here on Earth, and so we're going to look for Earth-like planets, right? And admitting that this is a bit limited, but it's at least a starting point that allows us to move forward. But we can detect planets now. We've detected more than 4,000 of these things, and so you might say, well, why do a good reasonable question would be, why do you need the theory about the existence of these planets when we can just go find them? Astronomers have detected them now since the mid-1990s. But I want to make an important point with you about this, is that the theory is absolutely essential to give us a framework to understand the observations, to extrapolate beyond those observations. For instance, those 4,000, more than 4,000 exoplanets that have been detected, they're all within 2,000 light years of the solar system. So, but the galaxy itself is 100,000 light years across. So how could we? How can you extrapolate beyond our limited little neighborhood in the galaxy without some understanding of the theory of how these planets form? My colleagues seem very keen to emphasize to you that science is empirical and science is based on observations. And I understand they want to distinguish this from much older lines of thought that were based on pure speculation. Armchair philosophy, we call it. Armchair because you're sitting in your chair and just thinking and not actually experimenting and observing the world. But I think when I'm talking to an audience that's born in the 21st century, many of you were born in the 21st century, you don't need to be told that science is empirical. You know that already. And but maybe you do need to be reminded that that theory is equally important as observations, because it's the theory that allows us to understand the observations, to put them in a framework that allows us to extrapolate beyond our observations. And so the framework that allows us to extrapolate or that the reason we believe there are lots of exoplanets, so planets beyond the solar system, is because we think the sun and the 8 planets of our solar system were formed together at the same time by one process. This is the principal reason, and so our observations are all supporting that theory that that planets and stars form at the same time in this one process. So that's going to be my first slide. Then is the observations that here in the solar system that support the idea that the solar system was formed together. So first of all, the orbits of the planets exist in a plane. So say we have the sun here in the center. We have Mercury going around, and then Venus, and then Earth, and so these planets are orbiting the sun in ellipses, and those ellipses lie in a plane, one single plane called the elliptic plane, that cuts through the sun and the orbits of the eight planets. So that's one key observation. Just to be totally clear, it didn't have to be that way, right? You could have had Mercury here, and then Venus like this, and then Earth like that, and Mars in a different orbit. But they're all 8 planets have their orbits in one plane called the elliptic plane. Furthermore, almost all of the 8 planets have their first let me say or just emphasize this point that with their rotation in the same sense. So not only are is Mercury going around in this sense, but Venus is rotating in the same way, and then Earth. It's not that Mercury is going this way and then Venus is going the other way. No, they're all rotating around the sun in the same sense. So that's another strong indication. We can make another point that the planets turn on their axes as they orbit around the sun, and the sense of rotation about their axis is usually the same as the sense of rotation of their orbit about the sun. I say usually because Venus and Uranus are two exceptions. But for the other 6 planets, the sense of rotation is the same. I think I have a better model of the sun here. I have my orange soccer ball, and of course I'm going to use the globe as my planet, the planet Earth. And I'm going to demonstrate first the prograde orbit of the Earth about the sun. So the spinning of the axis of the Earth is going to be in the same sense of rotation as its orbit about the sun. So here's the motion of the Earth about the sun in the annual cycle. And now here's the daily rotation of the Earth about its axis. And when this spinning of the Earth is in the same sense as its motion about the star, the sun, then we say the planet has a prograde orbit as the Earth does. Okay, now so that's the prograde orbit. Now let me contrast that with the retrograde orbit, in which the spinning of the planet is in the other sense of rotation. So now the planet spins the other way about its axis as it goes around the sun. So this is the retrograde orbit. So let me contrast the two. So here's the prograde orbit, and here's the retrograde orbit. Okay. Because the point is the retrograde orbits do exist. Venus is in a retrograde orbit, and Uranus is in a retrograde orbit. But 6 out of 8 planets are in prograde orbits, again indicating some organization that actually it's more than just organization. It's that they fit this will fit the model that we're going to discuss momentarily. But at this point, we can just say there's sort of an organization. There's another sort of observation that applies to the solar system, which I think in retrospect has been modified or downgraded in importance since we have discovered and examined thousands of exoplanets. But that organization, it's kind of obvious. Looking at the solar system, you have the rocky planets, Mercury, Venus, Earth, and Mars, that are the inner planets closest to the sun. And then you have Jupiter, Saturn, Uranus, and Neptune, the big gassy or ice giants that are all the outer planets. So you have 4 outer planets that are huge planets, and then you have these small rocky planets that are the 4 inner planets. So there's some sort of organization in there. It's like someone tidied up the solar system, or there's some fundamental reason why planetary systems form in this way. As I say, this latter observation has been downgraded in importance because of the observations of exoplanets, we're actually finding planetary systems with big gas giants that are, with orbits near where Mercury would be, sort of inner orbits. So that's well, I guess observations are important for updating our theories, but we still very much believe that planetary systems form together with their star. So let's talk about the initial conditions that lead to planetary formation. As we discussed earlier, the interstellar space is not completely empty. There's some medium between the stars. So we're within, when we say interstellar, we're emphasizing that we're in a galaxy, but between the stars. And this interstellar space has a medium consisting of gas and dust. And the constituents are, as we mentioned before, about 3/4 hydrogen and 1/4 helium, and then the other remaining elements are in proportion that I showed you, with oxygen being the most abundant constituent after helium, and then there's carbon, etc. And these exist in the form of either gas or dust, and that makes up about 1% of the remaining material is actually in the form of tiny grains of dust. So this medium is not completely uniform, but can collect in clouds. And these clouds, for some reason, start to collapse on themselves. The force, of course, pulling them in, causing them to contract is gravity. So why did they, when we say for some unknown reason, I don't mean to suggest that there's some big mystery here. It's just that there's some detail that led to that sparked this process. It could be as simple as two clouds collided with each other, which led to a higher concentration of dust and interstellar medium, which then triggered the gravitational collapse of this cloud. And another important factor we'll see is the rotation. So if you can, well, this will become more clear in a minute, but they might be rotating in the opposite sense, and when the two clouds come together, that causes them to slow down as they mix together, and that too would lead to a gravitational collapse of the cloud. I think the sort of let's just accept that we have a cloud that starts to collapse on itself, and it's important to bear in mind that this cloud of material, interstellar medium, has it's composed of many parts, so it'll have internal motion. The different parts will be moving in random directions, but you can always define an important physical quantity, which is called the net angular momentum. Now, without going into too much fundamental physics that most of you don't know, let me just say that you can calculate the average angular momentum, which is the tendency to rotate about an axis. This can be calculated for any cloud or any material, and we could calculate it for this collapsing cloud of interstellar media, and it would the important physical principle that applies is that this angular momentum will be conserved. It's conserved because there's no external agent trying to rotate it in one sense or another. Or to stop it from rotating. It's already rotating, and there's nothing to stop it, and so it will continue to maintain its net angular momentum. So the gravitation causes this cloud of material to contract, but eventually you can obtain an equilibrium in which gravity, the force of inward of gravity, is balanced by the centrifugal force, causing the material to want to move outwards about the rotation axis. So let's take, for argument's sake, that the rotation axis is in that direction. Then the force of gravity perpendicular to that axis of rotation will be repelled by the centrifugal force. The centrifugal force is very familiar to you. It's the force you feel when you're standing on the bus and the bus goes around the roundabout, and you're pushed outwards, right, away from the center of the roundabout. That's the centrifugal force. It's the same force that keeps the moon from falling down on the Earth, but it only applies about in the direction away from the axis. So if our axis of rotation was there, it's perpendicular. It's always perpendicular to the axis of rotation. So along the axis of rotation, the force of gravity is not impeded by rotation, and so the gravitational collapse continues down to a disk, and this leads to the flattening of this cloud along the axis of rotation, but and therefore the formation of a disk, conserving its angular momentum the whole time. So I really like this explanation because it uses fundamental physical principles of the attraction of gravity and the centrifugal force to explain the formation of this sort of giant centrifuge, a disk, which in the case we're considering is the disk called the protoplanetary disk. This disk it's still the interstellar medium of gases and dust. But it's been flattened into this disk shape. I like this because I've noticed that there are disks everywhere in the universe, right? There are disks here in the solar system, in the solar system itself is in the form of a disk. In the solar system, we have the rings of Saturn. Let me show you the picture of the planet Saturn with its famous rings about it. So they're in the form of of a disk. How did they formed by the same process that that I was just explaining to you, that there's an axis of rotation here for Saturn. I think you can see my mouse going along the axis of rotation, and then this so angular momentum about that axis was conserved as the material that collapsed to form a Saturn collapsed under the self-gravity of Saturn, or the material that finally led to Saturn. And this material that makes up the disk, a lot of it is ice water, by the way, so ice cubes. This material didn't fall in because it's in orbit. It's rotating around Saturn, and its centrifugal force is pushing it outwards, and meanwhile the gravity is pulling it inwards. So those are that's a disk. The rings of Saturn are a disk that formed by this process. The solar system itself, of course, is in the form of a disk. As I was saying, the planets are in this orbit with the sun in the center, and the planets are on the elliptic plane and in elliptical orbits. So we have this sort of elliptical disk of the solar system. More generally, this is sort of, the solar system is 4.5 billion years later from what was a protoplanetary disk that is you find around every young star in formation in the universe. And the galaxies themselves are in the form of a disk. So here's the Milky Way galaxy, but viewed edge on. And it's in a disk. It is a disk, and it's in fact most galaxies are disks. So here's our nearest neighbor, Andromeda, and Andromeda is 2.5 million light years away from us. So apparently you can see Andromeda with the naked eye, but it's very subtle. And you have to, it's only visible in the summertime, and it's faint, but it's not small. Andromeda is huge. In fact, it's 6 times the diameter of the moon. So imagine, the moon can look pretty big on the horizon sometimes. Andromeda is 6 times that big, but it's quite subtle, and you can only see it faintly under ideal conditions. But look out for Andromeda next summer. And as I say, most galaxies are disks. So this disk-like structure appears in the universe because of gravitational attraction causing collapse and angular momentum being conserved. And so there's gravitational collapse along the axis of rotation, and gravity is balanced by the centrifugal force perpendicular to the axis of rotation. If this applies on all length scales, you might ask, well, what if we go to the largest length scale? What about the universe itself? Today, we don't think the universe is rotating today. The standard cosmological model proposes that the universe is isotropic. So we can't have, by definition, we can't have an axis of rotation because that would give a special direction. But a rotating universe model was proposed by the famous logician Kurt Gödel. So Gödel is known for his Gödel's theorem, which is a pure logic theorem, which is important to mathematics. It's the Gödel incompleteness theorem that says formal systems are necessarily either incomplete or self-contradictory, which was problematic for mathematicians. And so Gödel was not even a physicist, but he was friends with Albert Einstein because they both worked at the Institute for Advanced Study in Princeton, New Jersey. And they became friends, and I guess Einstein taught him general relativity, and he came up with this rotating universe idea. So one can look that up under Gödel universe if you're interested.